I'm going to be talking about number systems. So the idea is, why do I need to talk about number systems? And how, after I represent numbers in various number systems, can I do some arithmetic with it, right? So computer is the answer to that. If I want to use a computer, I need to, which is a digital device, I need to be talking about zeros and ones. Zeros and ones belong to the binary representation, binary number system. But humans are very used to decimal number systems because we have got 10 fingers, 10 toes, and we have been using since elementary school a decimal number system. So the one main conversion that we need to look at is, how do you convert from decimal that we are so comfortable with to binary, so that we can understand how a computer processes data, how a computer stores data on a hard disk. It will all be in terms of zeros and ones. But there are other number systems that we are going to also discuss while we do this decimal to binary. So humans love this, right? Humans love the number system decimal. We have all seen symbols 0 through 9. So any number that you can make up using these 10 symbols or 10 digits, 0 through 9, will belong to the decimal number system. And what works in decimal number system is the positional number notation, also called as positional significance, meaning I can represent any number. So for example, 246, by adding weights of increasing powers of 10. So I take 6 multiplied by 10 raised to 0, 4 with 10 raised to 1, 2 with 10 raised to 2, and add them up to represent 246. So what do you see over here? You see 10, 10, 10, right? That is the same as 10 digits. So you see this number 10 repeating over here in the decimal number system, because the number of symbols or digits that are in this number system are 10, 0 through 9. And we have increasing powers of 10 going that way, right? So why is 10? So because it is base of this number system is 10. Or you can also call this as radix of this number system is 10, which is called decimal number system. Now 246, it is probably a good idea to understand what is this 2 and what is this 6. Can we call them the ends of the numbers with specific names? 6 is actually my least significant digit. The rightmost digit is least significant because that repeats the fastest, right? Because the next number is 247, 248. So that position changes more often. And in this particular number, say 2 is actually my most significant digit. So the leftmost will be most significant because it will change the slowest. It has a higher weight, 10 raised to 2. Now, how do you represent in base 10 or radix 10? You take each digit, n sub I, you multiply it with 10 raised to I, where I increases, right? So I over here is going to be greater than or equal to 0, and it is going to be an integer. So in the previous example, we had I from 0 and 1 and 2, and we added all of that up, right, to get the number. So n 246 was represented either as 2 and 4 and 6, where n i's, and we multiplied it with 10 raised to 0, 10 raised to 1, 10 raised to 2, and added those up to get our number. And you can do this for any number in the decimal number system. And not just for integers, we can also do this for fractions. The only thing that would change is over here, it stops at what? 10 raised to 0. Now, and then after that, you will have a decimal point. But after the decimal point, you can have some other numbers in the decimal number system. The other numbers also should belong to the same set of symbols, 0 through 9. But their weights will now be 10 raised to -1, 10 raised to -2, and so on. It'll keep going down in terms of the exponent. So for example, let's just do a quick one. How do I represent, say, 246? Let's see here. So if I wanted to do 246.35 in decimal, using positional significance, I can represent that as 2 10 raised to 2, 4 10 raised to 1, 6 10 raised to 0, 3 10 raised to -1, 5 10 raised to -2, right? That is your number. And what appears the most is decimal 10, right? They are all powers of 10. They increase on the left, they decrease as you go to the right of the decimal point. Now, what are we discussing over here? We are mainly focusing on unsigned, meaning only positive, unsigned integers and fractions, right? So that's how you would represent numbers using positional significance or positional number notation. This was a quick review, right? This was nothing new. I expect that everybody over here understands what we just talked about. Now, when you start talking about binary, which is what computers understand, zeros and ones, binary stands for two digits. What are they going to be? Not 0 through 9. I start at 0, end at 1. Those are the two, zeros and ones. So that's going to be my symbol set for binary number system. Every number in the binary number system can only have 0 and 1. Or it might have, so if you have a decimal point in the decimal number system, what do you think you will have in binary? Feel free to interact on the chat box. If there is a decimal point in the decimal number system, what do you think we will have in the binary number system? Binary point, absolutely. So what changes when you still using positional number notation? How can you represent any number n? The only thing that changes is the 2 raised to I. So instead of having increasing or decreasing powers of 10, now you have increasing or decreasing powers of 2. Where ni, each symbol can only belong to the set 0 and 1 because we are talking about binary numbers. But I itself can be greater than or equal to 0 for integers. And then if it goes less than 0, still integers, you will get fractions. And the same applies even for the decimal number system. When I is less, -1, -2, -3, that's how you are getting fractions. So how do you convert this? Let's do a quick example. How do you convert 111001, which is in binary number system, to decimal? You use positional significance. From any number system to go to decimal, you use positional significance, meaning you multiply with increasing power of the base. The base of the binary number system or the radix of the binary number system is 2. So you have increasing powers of 2 appearing over here. So you take each digit, each bit, right? Bit is what? Bit is binary digit. So you have many of them here. How many do you have? 1, 2, 3, 4, 5, 6. Represented in what? Subscript 2. That means base 2. The best way to do this is like this. I would say 1, 1, 1, 0, 0, 1, and then 2. So that there is no confusion about what is the number, what is the base, right? Base you express as a subscript. How do you convert this? Well, take each bit and multiply it with increasing powers of 2 starting from 0. And move left until you find your most significant bit, or MSB. Most significant bit, least significant bit. And when you add it all up, what do you get? You get 57, which is now in the decimal number system. So that's how you would convert from binary to decimal. So here is a question for you. If I need to multiply with increasing powers of 2 to convert from binary to decimal, what should I do to convert from decimal to binary? Multiplying with increasing powers of 2 to go from binary to decimal. Divide by powers of 2. Okay, so divide successively by 2. That's what we are going to do. If you divide successively, repeatedly by 2 and record the remainders, that's how you go back from decimal to binary. Successive division. So how do you convert from 57 represented in decimal number system to binary? We keep dividing by 2. 57 divided by 2, 28. What is the remainder? 1. We take whatever was there, 28 divided by 2, 14, remainder 0, and keep going down. What do you get? You get your remainders, recording the remainders. When you record the remainders, what do you have? You have, you read it backwards. 1, 1, 1, 0, 0, 1. That will be your number. So this is a way to quickly check. And where do you stop? You stop when the quotient becomes a 0. Multiplying with increasing powers of 2, dividing successively by 2, and recording the remainders. Right? So that's how you go from 10 to 2 and back to 10. Let's do an example over here. I have a number in binary number system that I want to convert to decimal, right? So this is a question mark here, too big. How do I do it? I'm going to use, for anything, any to decimal, I'm going to use positional significance. Positional significance, or positional number notation. What does that mean? That means that I'm going to take these numbers and I'm going to multiply them with increasing powers of 2. Hold up. So I'm going to take what? 1 times 10 raised to what? Over here, for this guy, it is going to be, the exponent is going to be what? 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. Over here, 2 raised to negative 1, 2 raised to negative 2. I don't need to worry about this because that is 0 times 2 raised to 1. But everything else I need to worry about. So I'm going to multiply them and add it together. So what do I have? 1 times 10 raised, not 10, 2. Plus 1 times 2 raised to 2, plus 1 times 2 raised to 0, plus 1 times 2 raised to negative 1, 1 times 2 raised to negative 2. 13.5, sure, that is 13.75, right? Yes. In base 10. So, you know, you have to do two things. Whenever you write your answer, you have to explicitly talk about which number system it belongs to, 10, And the other thing that you can do to keep a check of things is 1, 3, 7, and 5. They all belong to the decimal number system. So that checks out, right? Here, I'm going to ask a question. Could this number also belong to octal number system? Octal means base 8. Yes is absolutely right. Because for octal number systems, you have symbols 0 through 7. And 1 belongs to that set, 3 belongs to that set, 7 belongs to that set, 5 belongs to that set. So it is, now I hope you see why this 10 becomes so crucial now, right? Because without this 10, I wouldn't know whether this number is octal or whether this number is base 10 or whether this number is base 16. I don't know, right? So this is why your writing the base explicitly becomes extremely important. Let's go back. 56 to binary. What do I need to do? I need to divide successively by 2 and record the remainders. So this is how I like to do it. 56 divide by 2, right? 28. Sure. What is the remainder? 0. Divide by 2 again. You get 14. Remainder is 0. Divide by 2 again. 2 times 7 is 14. Remainder is 0. 2 times 3 is 6. Remainder is 1. 2 times 1 is 2. Remainder is 1. Now I've got everything that belongs to binary. So I can stop here. The number is going to be what? The number is going to be 111000 in binary. And you can check it, right? You can check it by simply saying, take this number. This is what? 1. This is 2. This is 4. This is 8. This is 16. This is 32. So you can check it by simply saying 32 plus 16 plus 8 is 56. So it checks out. Do you prefer if we keep it as a whole byte rather than just display bits? Now, so for now, you can keep it as the whole whole sequence together. But when we start talking about octal number system, or more importantly, the hexadecimal number system, that's when I want you to focus on separating the bits out in groups of 3 or groups of 4. For now, you can display all the bits together. Let's talk about hexadecimal number system, which is a very nice and convenient way to represent binary, essentially. And the way it is convenient is because it's very compact. I can take 4 bits binary digits and express them as one hexadecimal digit. Hex corresponds to 16, base 16, or radix 16. And it usually starts with the representation 0x followed by the hex number. What are the digits that belong to this? 0 through 9, same way as decimal. I need to go all the way to 16. I ran out of numbers, so I'm going to use letters instead, A through F. So any number that can be represented as a combination of 0 through 9, A through F, is going to belong to the hexadecimal number system. Hex A through F, what they are representing is decimal values 10 through 15. That's it. So each hex digit is going to represent some decimal value. 0 through 9 represents 0 through 9. A through F represents 10 to 15. How do you use positional significance here? Increasing powers of 16. Can we have fractions? Absolutely. When you have 16 raised to negative 1, 16 raised to negative 2, that's when you are going to start seeing fractions. But each number, again, the same way, right? Representing the numbers using positional number sequence helps you to go from any number system to decimal. So suppose you are doing this example. This number 8A9B represented in hexadecimal number system. How do you know what is it in decimal? Well, take each hex digit, B, 9, A, and 8, multiply them with increasing powers of 16, increasing powers of the base, and add them up. When you do that, you have got the number in decimal. The only thing that was tricky over here was because B is a hex digit, we are going to represent that using its decimal equivalent of 11. Same applies for A. A is decimal 10. Quick question. How do I go back? To go from 16 to 10, I multiplied each digit by increasing powers of 16 and added it up. Divide by 16, absolutely. Successively divide by 16 and record the remainders in the reverse order. The same way we did for binary. The only thing that changes is what? This will change to 16. That's it. We are still doing that same thing. And when you divide by 16, you cannot have a remainder greater than or equal to 16. You will have a remainder that is less than 16. So it will have to belong to the hex number system. But when you do that, after you divide, you will get numbers, right? You will get 11, you will get 12. For 11, you write B. For 12, you write C, and so on. How about octal number system? Yes, you can do that. 0x, 8a, 9b is fine. Octal number system, what are the symbols? 0 through 7. The symbol set is going to be 1, 2, 3, 4, 5, 6, and 7. That's it. 8 of them. Let's do a quick exercise of counting in octal. How do you count in octal? Add a slide. Oh, do I have this? No. Let's. Oh, no. Let's do a count in octal. Zero, 1, 2, 3, 4, 5, 6, 7. All right, what's next? 1, 0 or 1, 1? Which one? 1, 0, yes. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. What's next? 2, 0 is perfect. You guys get the idea. All right, let's do a counting in hex. Zero, 1, 2, 9. After 9 comes what? A is fine. Good. B, C, D, E, F. What comes after F? 10 is beautiful. 11, 12, 13, 19. After 19 comes what? 1A. Very good. 1F. After 1F comes what? 2, 0. Perfect. All right. You guys get the idea. Okay, let's now, so in that case, let us do one more. Count in binary. Zero, 1. What comes next? Okay, what comes next? 11. Okay, what comes next? Yes. Oh, they cannot be 2. They cannot be 2. You can only have zeros and ones in a binary number system. Yes, 1000 is good. Now, notice something over here. The least significant digit alternated. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. The next bit to that, well, I suppose I can write zeros without any problem here, right? The next to that, it was half the frequency, 0011, 0011. And the next, or in this case, the most significant bit was what? I can always add zeros to the left. That's fine. I don't change the number. 4 zeros, 4 ones, right? So you see how it is going. The rightmost bit is repeating 01, 01, 01. To the left, it is 0011, 0011. To the left of that, 4 zeros, 4 ones. To the left of that, 8 zeros, 8 ones. To the left of that, 16 zeros, 16 ones, and so on. It keeps going. So if you wanted to fill out a table, you can do this in minutes. You can just say alternate, have the frequency, have the frequency, have the frequency, and keep going left. All right, let's continue with our examples. All right, base 8 to decimal. How do I do this? I think somebody already answered, but let's do that. 8 to 10. Anything to 10, positional significance, right? Multiply by increasing powers of 8 and do it. So I'm going to do right here. 4, 8, 0, 1 plus 7, 8, 0. 3, 8, negative 1. 1, 8, negative 2. What is that equal? Let me just do this calculation in my head here. I think it is 39.390625 in decimal number system. All right, you can check my math later. Okay. So increasing powers of 8, right? Let's move on. We did the counting exercise. Let's do this. How do you convert base 10 to binary? Now the number is a fraction. So we need to be a little bit careful because we cannot simply just, if it was just 56, we would just keep dividing it by 2. But because we have a 0.34, then we need to deal with it slightly differently. So I'm going to do this in 2 separate parts. One is going to be my integer part and the other is going to be the fraction part. So let's do the integer part here. And fraction part here. And for 56, base 10, what do I need for 56? I need 32, I need 16, and I need 8. That will make 56. So that means I need the 5th bit, the 4th bit, and the 3rd most significant bit to be ones. So my number should be what? 1, 1, 1, 0, 0, 0. Right. That's the integer part. That's easy. Divide successively by 2 and record the remainders and you get it. But for fraction part, you need to adjust it a little bit. So for example, the fraction part here is 0.34. I'm going to, instead of multiplying with decreasing powers of 2, now I'm going to successively multiply by 2 and record the integer part of the result. So what do I get here? I get 0.68. So I'm going to fill in this 0. So let's see. Later we'll do that. 0.68. Next, 0.68 times 2. What is that? 1.36. Okay. Drop the integer part. Take the fraction. 0.36 multiply by 2. What do you get? 0.72. 0.72 times 2. What do you get? 1.44. Drop the integer part. Take the fraction. Multiply by 2. What do you get? 0.88. And this keeps going. Never ending. It keeps going, right? It may end. It may not end. Depends on the number. So what is it? What is the answer here? The fraction part was easy. 1, 1, 1, 0, 0, 0. After that, you had a binary point. And after that, you had 0, 1, 0, 1, 0, and so on. So 0 went here, 1 goes here, 0 goes here, 1 goes here, and then 0 goes here. it can keep going. So in some cases, we might have to limit the number of digits that you have for the fraction part and the integer part, right? But the process was what? Multiply by 2, keep recording integer part of result. So I suppose I can ask you this. If this question was base 10 to base 8, what would I need to do for the integer part and for the fraction part? So instead of this, if suppose this was 8. So for the integer part, I would be dividing it by 8 and record the remainders. Yes. And for the fraction, I would multiply by 8 and record the integer part of the result. You got it? Yes. Can there be other number systems? The four most common ones are what? Decimal 10, binary 2, octal 8, hexadecimal 16. But there can be others. They can be base 5. You can actually create your own base 4, base 17. You can define your own number system. All you would have to do is define the number of what kind of symbols it will be made up of. For base 10 to base 5, what do you do? What do you do for base 10 to base 5? I'm going to do 56 divided by 5. First, for the integer, I get 5, 11, 55, remainder is 1. And 5 times 2 is 10, remainder is 1. So my answer is going to be what? 211. 211 base 5. That is going to be my integer part of the result. And for the fraction part, I need to successively multiply 0.38 by 5. I get 1.9. I drop 1, take 0.9, multiply by 5. I get 4.5. Drop 4, take 0.5, multiply by 5. I get 2.5. I drop 2, take 0.5, multiply by 5, 2.5. And after that, it is going to be in a pattern, 2, 2, 2, 2, 2, 2, 2. So my answer is going to be what? 211.142222, so on. Now you see, all these digits are belonging to base 5, right? 0, 1, 2, 3, 4. That's base 5. Every number over here belongs to that set. So that's something that you should do. After you write your answer, quickly check whether it is a base 5 or not, whether it's an octal or not. Right? You don't want to do this, 89 base 8. That would be horrendous, right? That is clearly a wrong answer. So you can quickly find that out by checking your work, right? Just by looking at the answer. How do you go from base 16 to base 10? Over here, I have a fraction as well. So I'm just going to do this over here. 8 times 16 raised to, using positional significance. I have that 10 raised to 16 2 plus 9 to 16 1, 11 16 0, 12 because I have B and C. So B is 11, C is 12, 16 negative 1, and 15 for F, 16 negative 2. And I don't know. I can't do that math right off the top of my head. You guys can do it after that. So that would be your answer in base 10, right? Just by plugging in those numbers into a calculator and finding that out. On future assignments, you will indicate the number of decimal places needed. Yes, absolutely. I have to. Otherwise, there's no way. I have to. Base 10 to base 16. This example should be pretty easy. Take 46, divide by 16. What do you get? 2 times 16 is 32. What is remainder? 14 is the remainder. 14, what should I write instead of 14? It should be a hex. E is absolutely right. So my answer here is what? 2E. Question. So why don't we use the scientific notation method for bases 10 to 5 on the last example? We did, right? You see, we took 56, divided it by 5 and recorded the remainders. And we took the fraction part, 0.38, and kept multiplying by 5 to get the number in decimal base 5. So that is actually using positional significance. No. Just so I would recommend just do this. 2e base 16. So let's talk about bases for now. You could actually do that. You could actually write 0x2e and you would be right. But just so that there is some sort of consistency in your answers, write the base of the number system as a subscript. So they both work. Yes, they both work. Okay. How can we do this? Convert 157 base 9 to decimal number system. What should I do? Using positional significance, I'm going to take 7, do this, 5, 9, 1, 1, 9, 2. I think 7, 45, 81 should be 1, 3, 3. Increasing power of the base and add them up. Multiply each digit with increasing powers of the base and add it up. No matter what base, right? Right now it's 9. It could be 5, it could be 4, it could be 11. 45. Okay, so let's do something interesting here. How can I make 45? I can make 45 by using 32, and what else do I need? I need 8 to reach 40, and I need 4 and 1, right? So I'm using numbers that are powers of 2 here, right? So I've got what? The answer should be 1 in the 5th position, 0 for 16, 1 for 8, 1 for 4, 0 for 2, and 1 for 1. That's your answer. So as you are working with these, you will get more and more comfortable with how to use. So you don't have to divide, right? Like you could have done this, you could have done that, but this is a quicker way to get the correct answer as well. And you can check it. Multiply this with 1, 2, 4, 8, 16, and 32, and add it up. You will get back your answer, your number 45 base 10. All right, so here, are we out of time for this class? Unfortunately. Are there 9 minutes left or not? Yeah, sure. All right, let's see. Let's stop and at 11:50. Sure, the fun has to stop here.